Alright, this video is like a You're Telling Me series. Maybe that's the name of the series, the name of the video, but when it comes to mechanical engineering, maybe not even mechanical engineering, I'm talking about strength of materials. So, that's a course in college, that's for engineers. But anyway, everyone should know how strong something is. And let's just get to the point. So let's say you have an I-beam, but it's not supported at both ends. Like it's just welded to I don't know. Let's say it's coming out of a building. You know what I mean? And it's like a big old awning. And it's like for a big old library. In Bozeman, Montana, there's a big old library. And it's got a big old awning, I think. And maybe there's big old I-beams sticking out. Now, in that situation, maybe there would. But for our situation, let's say they're steel. And if they're an I-beam, well, they're shaped like an eye. They have a flat top, a flat bottom, and then well, I'm just going to say they have a web. Now the web is the middle part. Sometimes it's good to use terminology, and sometimes it's just good to make up your own. But I couldn't make up a term for what the heck the middle was or the web was. So I just used the correct terminology. So anyway, maybe the top and bottom are called flanges. I think that's what they're called. Okay, so, you know, if I had to make you scroll to the end of this video, I would say, well, look, the thing's coming out and it's hinged. Just imagine it's hinged to the building. What do you mean it's hinged? Well, just imagine there's a hinge at the bottom. And if it's just hinged at the bottom and you let go, well, it's going to fall to the ground. But it's still going to be hinged to the building. Does that make sense? Yes, it does. In my mind, I just visualize it right now. So that's why it's good to make a video where now you just have a mental image in your head. You have this big old library in Bozeman, Montana. You got this big old I-beam. Flange on top, flange on bottom. And it's got a hinge, I guess, on the bottom flange. And then when you let go, the thing just kind of fell to the ground. Now, just for a visual, let's say you put the hinge on the top. Would the thing fall to the ground? No, because it's hinged on the top. The bottom is like pressing into the building. Okay, so you're telling me that the bottom of the I-beam is actually like pressing into the building, doesn't even need to be connected, but I have a hinge on the top and it's doing its thing? Yes, and that's a very good visual because the bottom of a bridge or an I-beam or a beam, that's just the general term for beam, bridge, I-beam, whatever. The bottom's in compression. And that just kind of proves I could end this movie right there and be like, wow, I learned something new. Let's say I have like a big old I-beam sticking out the building, big old library, and I just, connect a little hinge, little metal hinge, whether I welded it or bolted it on. But the hinge is just at the top. And sure enough, you know, that I-beam's not going to just fall down. It's going to support itself. And the bottom's it's going to be kind of constantly pushing into the bottom. That's probably going to push into the bottom a little more than near the top, near the hinge, just because we know a little bit about leverage. Um, but this was, yeah, so let's introduce that term. So, yeah, leverage. So we got our hinge at the top, and then let's say we put some weight on the end of that I-beam. Well, where's all the leverage going to be? Well, it's going to be at the farthest point from the hinge. Okay, so now we're getting somewhere. So let's say I have I don't know, let's say this I-beam's like 1 foot thick, 1 foot web, flange on top, flange on bottom, and it sticks out 10 feet. And I go and pull on the end of that I-beam with the hinge on top. How much leverage can I, put into the bottom in compression into that I-beam? Well, let's not even use our brain and just say, let's say 10 times as much. So if I pull down one, I don't know, just one person, one of me, then the compression at the bottom of that thing might be 10 of me. Does that make sense? That's leverage. Okay, so now you got this good visual, and I think we can all understand that. And it's just like, wow, I kind of learned two new things that I never knew that I thought I would knew. But that's not even the golden nugget of this video. Because let's say we put the hinge on the bottom now. Wait, but if we just have this section of I-beam and we butt it up against the building and then put the hinge on the bottom, and then here's a better visual. Let's say, for whatever reason, we got a little nubbin of I-beam sticking out the building. So for 1 foot, you have this, well, it's a 1 foot tall I-beam, 1 foot tall web, maybe a 1 foot wide flange. So it's 1 foot wide, 1 foot tall. It's a square I-beam, but it's shaped like an eye. And it sticks out at the building 1 foot. Alright, it's a lot of ones, but I guess I visualize this nubbin of I-beam sticking out the building. Now, I got a 10-foot I-beam. That's my canopy. I don't know if you call it canopy, but for a building, you want to do a little canopy. So you're going to do a 10-foot I-beam sticking out the building. You already have that 1 foot nubbin. But yeah, I don't want to make this too confusing. But we're going to make it 11 feet. So you have this. So what you have is you're going to crane in to position a 10-foot long piece of I-beam out that nubbin. And how you're going to connect it? Well, just like we said with a hinge. You put the hinge on the top, nothing's going to happen. It's going to be a lot of force. You'll be like, whoa. It's like if I just hinge the top, now you understand. See how like your brain's working now? You're like, wait a minute. I see where you're going with this. But yeah, the hinge is topped. And then you put a bunch of weight on it. You know what I mean? Put a bunch of snow. You supported some more pieces of wood and, made it all like a canopy. So it's like real heavy. And yeah, you pull down on the end of that canopy, you know. And yeah, so the hinge did its thing. But where's all the leverage going to be? Well, it's going to be at the bottom. And it's going to be pushing into the building. You know what I mean? We call that compression. And how much is it going to be in like multiplication? Well, it might be 10 times. Pull down one, you'll get 10 times. So yeah. So if you pull down a lot, you'll get 10 times a lot in compression. Okay. So now we have that visual. We got the little nubbin sticking out. So now we're going to take our 10 feet. Excuse me. We're going to take our 10 feet of I-beam, stick it up against that nubbin. And where are we going to put the hinge now? Well, we're going to put the hinge at the bottom. And I imagine that you can visualize that that I-beam isn't going to hold itself up. The hinge is on the bottom. It weighs a ton. I don't know. But when you let go, it's just going to hinge all the way down to the sidewalk or the walkway, under the canopy that you're trying to build, into this library in Bozeman, Montana, because it's a big library. Okay, so why'd you even give me that visual? Makes no sense. It's not even holding itself up. Well, now let's say um, just by welding or for some magic that you were able to, hinge that I-beam like back up, push it back up into its spot. So you have the nubbin sticking out, the hinge on the bottom, the eyes, once you get them together, they're all lined up. And now you're gonna put some duct tape. This is a good visual. I just kind of going on the fly. I'm like, how am I gonna show you how to visualize this? Well, you know, on the top of that I-beam, you're just going to put like a bunch of duct tape, just in strips all the way across. So duct tape's about 2 inches wide. So you're going to do like 5 strips of duct tape, maybe 1 foot long, maybe 2 feet long. You know what I mean? Because you want that duct tape to stick. And so now you let go of the I-beam. Obviously, the duct tape just ripped. But let's say you slowly let the I-beam take its own weight. What's going to happen to that duct tape? Well, it's going to take its weight too. So that duct tape's going to stretch out. See, does that make sense? And I think it does. I think you already know where this video's going, and you're like, David, you're blowing my mind. That's 3 things I never knew about I-beams. I just imagine if you just threw some sort of I-beam up there, it's like strong, and you just call it strong. It's metal, it's strong. Never in my wildest dreams would have been like, oh yeah, like the little I don't want to go into it. I'm not going to say the little molecules, are getting stretched out. Each molecule's like a little strip of duct tape. But anyway, so our five little strips of duct tape, they're going to stretch out. And what's going to happen to them? Well, they're going to break, but they're going to take some force. So now, instead of five strips of duct tape, we're going to put 10. You know what I mean? And keep layering it up. So now we're going to have a layer of duct tape so thick, it's as thick as that flange. Well, David, that was interesting because now I can visualize that. Oh, you know what? I'm going to break the fourth wall. I'm saying my name's David. But maybe I'm going to switch it up. I'm going to be like Dix because that's this character's name. Okay, I'm going to build up my fourth wall again and get right back to it. All right, so I asked myself, Dix, where am I going with this video? Well, just continue on, Dix. It's going to be all right. All right, so I was telling the good people at home, that's you guys, that if I put all these strips of duct tape on top of this I-beam that's hinged at the bottom, I got so much duct tape as thick as the flange that's kind of like underneath the duct tape. And I think we can all visualize that. Now we let go. And this is going to be a problem for, you know what I mean? I bet you if you got so much duct tape, 2 foot long strips, piled them so high and thick that they were just as thick as that I-beam. And let's just guesstimate. If this is a 1 foot by 1 foot I-beam, I bet you those flanges are at least a half-inch thick. Okay, so we have half-inch thick, just like strips of duct tape. And then when we let go of the weight of that I-beam, now it's 10 feet long. And I'll just key it in. A 1 foot I-beam, um, you know, that, that thick for the flange and the web. Well, you go look up your I-beam chart. There's another little nugget of gold. It'll be like, well, this is a 12, like a 12W20. It means that it's like 12 inches wide, or 12 inches tall. So like one of the dimensions is 12. Gives you a little heads up. But then what's the W20? Well, that means that that's its weight, 20 pounds. Well, you're saying this I-beam is 20 pounds? Well, we have 10 feet of I-beam. So it's 20 times 10. So our I-beam is 200 pounds. Okay, now I see how that works. I could say it again, but you have 12 by W20. That means that for every foot of I-beam I have, I got 20 pounds of steel. Okay, that makes sense. All right, so I've been learning like 4 things in this video, and you're just blowing my mind, Dex. You know what I mean? So it's just very interesting. And my question, that would be a viral video. Is the weight of 200 pounds, you know, kind of pulling down the heavy side of that I-beam is hinged? Is that gonna Is that enough duct tape to hold that thing? I'd probably say yeah. I bet you it would. I don't know. You know what I mean? On a hot day, you get that duct tape to stick. Maybe even let it set up for a day. Really do its job, and then let go of all the weight. I bet you'd hold that I-beam up. That's exactly what we're getting at. Because just because it's held up doesn't mean that duct tape isn't stretching out, because that duct tape definitely wants to stretch out. That's a lot of force, and I think you can visualize that, and I think you can see where we're going. So basically, you're telling me that if I have an I-beam sticking out of a building, it's exactly like it's hinged at the bottom, and then you just duct taped a bunch of duct tape on the top, and it's just pulling on all that duct tape. Well, now I'm just going to make a magical leap and say exactly yes. So now I'm saying that you can use this little nugget of knowledge and actually do a very quick calculation, even in your head, about how strong that I-beam is and how much weight you can put at the end of it. Well, how are we going to do that, Dex? I'm going to break the fourth wall because, I don't know, I'm just not used to saying Dex. I kind of like to say David. It's like Maybe it's like it is a multiple personality. Like this is Dex, but then I'm talking to David. You know what I mean? It's like two different people. You're like, who's David? Well, we kind of know who that is, but we also know who Dex is. So for this video, I might go back and forth. All right, get out my trowel. I'm going to build up that fourth wall again. All right, so now I see where you want me to get in this video. David, well, Dex, yeah. So Dex, you want me to know how strong an I-beam is sticking out of a building. Yes, I do. And so let's set up some parameters. So if I have this library, big old I-beam, and we call it a cantilever maybe, sticking out the building, how much weight can we put on the end of it? Well, let's say we could put on one of the I-beams, let's say we could put a whole car. Like 4,000 pounds? Well, that sounds like a little bit much, but maybe not. I mean, you only have 10 feet sticking out, and it's a 1 foot by 1 foot I-beam. That's a huge amount of steel. Even though the amount of steel only weighs 2,200 pounds, I bet you it could easily hold 1,000. I mean, I'm sorry, I'm getting ahead of myself. I bet you it could easily hold a ton. So is that a good place to start? Like 2,000 pounds? Well, maybe, but we want to make whatever we're doing, we want to make the calculations a little simple in our head. So we'll see what we do. But now, since we have a number, 2,000 pounds, and it's 10 feet away, what's the leverage on that duct tape? And let's go back to our example. Let's say I pull down 1 of me. What's the leverage on the duct tape? We were going to say it's 10 of me, right? I mean, just by using maybe the common sense in our head. We're like, if I pull down on that duct tape, because I'm 10 feet away, and that duct tape, so now let's take a look at why that duct tape would have 10 times me being pulled on it. And I think you already know. And I think you're already like, wow, this is like the 5th cool thing I've learned in this video. So, hopefully I can only count on 10, 10 fingers. So, don't blow my mind, okay? That's kind of funny. All right. So, where we going? Yeah, 10x. So, yeah, you can see if I pull down on that I-beam 10 feet away, that duct tape, sure, it's gonna like get pulled 10 times what I weigh. So, all right. But why is that? Is leverage. All right. So let's measure from the hinge. So we have a hinge, and let's just say the hinge is our leverage. Okay, I can buy that. And I'm 10 feet away from that hinge. I'm pulling down with one of me. Okay, how far is that duct tape away from the hinge? Well, it's only 1 foot. And isn't that a tenth of like how far I'm pulling down? Yes. So shouldn't the force on the duct tape be only a tenth? Oh, see, I'm using my own logic to kind of scramble my brain, and I was doing that on purpose because that's not how leverage works. That's how engineering works. You're just like, well, I'm using numbers, using proportions, using equations, and pretty soon you're just going to do the wrong thing, get completely the wrong answer. So in our example, I'm pulling down with one of me, 10 feet away, but we know leverage multiplies, you know, and that hinge is only 1 feet away. So we just know by using how leverage works that the force in that duct tape is going to be 10 times. All right. Now, that little nugget might not blow your mind, might even confuse you because you're just like, whoa, you said it was 1/10, and then I saw where you're going. But then, the nugget of gold there was like, sometimes you need to just guess, so you actually get the right answer in the end. Because else, if you just do the calculations, you're going to do them wrong. And you're going to get a number that just makes no sense. All right, we're almost there. Because now, instead of just one of me pulling down on this, it's an awning for a library, in a big old library, 10 feet out, which isn't that far. Like, that's not a big cantilever. And we have like a 1 foot by 1 foot big old I-beam. So it should hold quite a few pounds. And we're going to say each I-beam sticking out can hold 2,000 pounds. So now, very simply, turning off your brain, what's the tension on that duct tape? Well, it'd be 10 times 2,000, which would be 20,000 pounds. Now, is that duct tape going to hold 20,000 pounds? No. I think we can all agree on that. But now, we're going to say, instead of duct tape, we're going to fuse that metal together with something that's been around for over a century. I think. Oh, no, no, no. I guarantee. Maybe not 2 centuries, though. It's still a new technology, but it's welding. So, if I get rid of that duct tape and then notch a little V. So the only thing that's holding that I-beam up is that hinge. And if I let go of the hinge, it's going to hit the sidewalk. But someone pushes that I-beam up into position. And then I carve out, a little V in the top of that flange and then lay a bead. Basically, I'm melting metal and adding metal at the same time. I'm fusing and adding in this thing we called welding. And it's just all molten metal, high electricity. It's just good to know kind of what welding is. You know what I mean? It's just like I'm forging. It's not forging at all, but I think it's just good to get whatever in your imagination you know about. Um, you're just creating metal. You're like, you know, Jesus on the, or I mean, like God on the ninth or 10th day. You know what I mean? Like, you know, on that Monday, maybe not the Monday, but maybe Tuesday, he invented welding. And he's like, and now I will fuse these metals together. But not just fuse them together. I'm going to fill in the gaps and make a bridge of metal that connects one of those flanges at the top to the other flange. And guess what? That metal will be indistinguishable from the metal that got made. See? So you have metal on the flange at one side, and the fact that you're adding this hot metal with electricity. You're doing it so well. It's like no one can even know that where that metal began and where it ended. And it's just good to know that that's what welding is. It's not glue, it's actually creating metal to metal where no one can know what you even did. And, that's why there's, oh, that weld's probably stronger than, the actual metal. Well, sure. Because if you just got mild steel, well, the strength of it's maybe only going to be as low as like 30,000 pounds. And maybe it's going to be as high as 60,000 pounds. I could say I don't know, but I do know. Those are kind of its ranges. But when it comes to welding, you're going to use rod that's like, well, this is 70-14, or this is 60-11. You know what I mean? And it's been a while since I've done some welding. Or I don't do stick welding. I just, do my little plug into the wall, little easy bake oven welder. Keep it simple. Now I'm a real welder, mentally, but I guess, you know, I haven't done too much stick welding. But when you come to the sticks, you get that, 60-11, 70-14. Hopefully I'm saying those right. But what's the 7 and what's the 6? Well, the 7 means it's 70,000 pounds. So you're telling me that welding rod's as strong as 70,000 pounds? Yes. Didn't you say that mild steel, when it gets made for that I-beam, might be as low as, 30 or 40,000 pounds? Yes, it can be. So, maybe that goes into the consideration that, yeah, your weld's going to be stronger than the steel you're welding. Okay, so that was a little side tangent. But when someone says your weld's going to be stronger, I think it confuses you. Because all you're going to be thinking is you're like, well, you're just using stronger glue. And maybe that is a good analogy. You are maybe adding stronger metal to bond the two metals you're putting together. I don't know. But it's just good to visualize things so you kind of understand what the heck they are. But now, all we did was weld the top flange together. So now the web still has like a ½ inch gap. We got the hinge on the bottom. And now that welded flange is just like our duct tape. So we're going to put our body weight on the end, just one of us, and that welded flange. Well, isn't that going to take the load? And yes, it is. But you see the confusing part now. You're like, Dex, I've always thought that like when you had, something made out of metal, any little part of it seemed like it was the whole. Well, yes, it is, and all those little parts are getting pulled just the same. That part's farther away from where we're pulling, so it's going to be, maybe the most. We can kind of maybe see that. I don't know if you can or not. But the same thing happens. It's going to get pulled with 10x. It's no different than duct tape. But it's just so interesting when you were visualizing the duct tape, you were like, yeah, that duct tape can get ripped in too. But now that you welded all this metal, now you don't even think twice about it. You're just like, I don't know. Yeah, it's like you lost me because it seems strong. But now you can imagine if we pulled down really, really hard. Maybe it's the hardest we've ever pulled down. Maybe you like go take a bulldozer, well, or like I mean, that don't make no sense. But go take like an excavator and then go, the little bucket and start just pulling down on that with all the hydraulics. I don't know. But you can imagine what you got to visualize is that welded strip of metal holding that flange together is like just pretend that's the duct tape now and it's going to get stretched out. How much can it take? See, because you already just thought it's strong as strong when you welded it. But no, if it's like the duct tape, at some point that duct tape's going to rip, and at some point that top of that flange is going to rip. Okay, I think I know where you're going with this. I can understand that. So that might be the sixth thing in this video. I don't know what we're at, but little gold nugget. It's like, yeah, now you're closer to blowing my mind. It's very interesting. Okay, but how strong is metal? Well, no one knows except I know, and I just get so frustrated that no one knows. All I have to say is it's 50,000 psi, and maybe it's, well, there's a couple ways to do this. One is because this is the hardest part. This is where like I need like maybe a 5-minute tutorial, but I'll just give you the answer. So steel is 50,000 pounds per square inch. See, that means nothing. 50,000 pounds per square inch is also 50,000 psi. But when it comes to that number, I understand. It's not going to make any sense. 50,000, that's like not a huge number, not a small number, but it's pretty big. It's big enough where I'm just like, I don't have any reference for 50,000 pounds. I don't know what 50,000 pounds is. Well, let's just say my Dodge Caravan, it's white. It weighs 5,000 pounds. How many Dodge Caravans would I need to get 50,000 pounds worth of Dodge Caravans? Well, I'd need 10 of them. So hopefully that was pretty easy. But that's how much 50,000 pounds is. So how does that relate to the strength of steel? Well, if I have 1 square inch, because it's 50,000 pounds per square inch, if I have 1 square inch of steel, it's as strong as 50,000 pounds. It's as strong as 10 Dodge Caravans. Well, what the hell does that mean, strong as 10 Dodge Caravans? Well, let's say you put 10 Dodge Caravans, in a big old, like, I don't know, in a big old crate, shipping container, I don't know, but it still weighed 50,000 pounds. And then on the top of that crate, you put a little hook and, something to lift the whole thing up. You're going to try to lift 50,000 pounds up. Now, is that a lot? Well, I don't know. Let's compare it to a train car. I think a train car might be 100,000 pounds. You know what I mean? Next time you're at stop by the railroad track, be like, oh, this is cool. I'm gonna learn something new. I'm gonna read the numbers on the trains as they pass by, and you might see they, kind of weigh like 25,000 pounds, like empty, maybe like 90,000 or 80,000 pounds full. But some of these train cars can easily hold 100,000 pounds. That's what I thought, and maybe even more. You know, the biggest of the bigs can probably hold 100 tons. So that would be 200,000 pounds. And I think that might be a high range. Maybe it's too high. But I think an engineer, because I was like, well, I was reading the numbers and it said 80,000. Like, but then I went up, I was taking some clients rafting. And this guy, he was like, he knew a lot about trains. He was like, he was in the business. That's what he did. And he's like, no, you got it wrong. They can hold more. I thought he said they could hold 100 tons. And it just made sense. Just a nice even number. 100 tons would be 200,000 pounds. And that makes sense to me from the engineering perspective because I looked it up, the actual engines. Now, those are heavy, but I know the actual engines, you know, those can weigh up to like 360,000 pounds. And I just kind of remember that number because it's pretty close to 365. And I'm just using some number association. That's like how many days are in a year. But one of those engines, 365,000 pounds. And yeah, so these fully loaded train cars, shoot, 20,000, 200,000 pounds? No problem, right? But that might be its upper limit, 100 tons. So anyway, we only have 50,000 pounds and we want to lift it. So back to lifting our crate of 10 Dodge Caravans. How are we going to lift that crate of 10 Dodge Caravans? Well, we're going to, we're not going to use a chain, not going to use a cable. What we're going to do is take 1 square inch of steel and weld it to the top of that crate. So this crate's metal, so that'll be helpful. All right, what are you talking about welding 1 square inch of steel to the top of this crate? Well, let's say we have you can imagine like a metal rod. You're probably imagining like a circular rod. Well, let's just get to it. This is going to be a square rod. But you can imagine a metal rod that's round, maybe a 1/2 inch rod. We've all used those. Maybe, I don't know, you can buy them at Home Depot. 1/2 inch rod, threaded rod, right? Um, but let's say you had a 1 inch, threaded rod, or just 1 inch round rod of steel. Okay, I can imagine that. Now, is 1 square inch, is that going to be thicker? Yes, it is. But anyway, but you can imagine having a square rod. You know, I don't know even know if you call it a rod. But anyway, it's square and it's 1 inch by 1 inch. And it doesn't matter how long it is, but let's say it's like 4 feet long. You know what I mean? And now we have this like, 4 foot rod, and it's going to be at the top of this crate filled with Dodge Caravans. And we're going to just weld this rod right to, right to the top. But we're going to do it right. We're going to um, we're going to taper it all in, and then we're going to weld like it's perfectly fused. Basically, there is no difference between the metal crate and that 1 inch rod. Like it's just perfectly welded, fused together. Use whatever in your imagination. So now we're pulling up on this rod, and we want to know if that rod's going to break. Well, it doesn't seem like it's going to break. You're telling us that you're going to pull up on it. But let's say we made it less. Let's say we only used like a 1/2 inch rod, 1/2 inch square rod. Would that break? Yeah, right now you're like, heck yeah, because I get it. Because you just said I can only hold 5,000 pounds. No, I'm sorry. I can only hold 50,000 pounds per square inch. And in this scenario, we only have 1/2 inch. It's going to break. So let's go back to the 1 inch square rod. And I'm just gonna say it's not gonna break. It's gonna perfectly pull all those Dodge Caravans off the ground. And yeah, yeah, as long as you don't like bounce that rod up and down and increase the weight, you can just do that for as long as you want. So that's as much weight as you can pull. But add another Dodge Caravan, that square rod, 1 inch rod, is gonna break. So now we have this idea that a material can be strong, but then at some point it's going to break. And that's good to know because you get so material is strong, how much can it hold? You want the answer, and then you want the answer that if you added more, it's probably going to break. And at the end of the day, then you can make the rod stronger or wherever. But you see where we're going with this. So now we can use it to figure out how much weight we can put on that flange. So we said our flange, we said our I-beam was 12 inches by 12 inches, and our flange thickness was ½ inch. So just like we piled up all that thickness of duct tape, how much thickness of weld did we weld into that flange? Well, it shouldn't be too hard. Let's turn off our brain and just kind of guess. Well, you said 12 and it was half, so it's like 6 inches. So you have 6 inches of steel. Does that make sense? Now let's go back and make sure it makes sense. We have this I-beam that's 12 inches wide, and that flange that we welded is ½ inch thick. So yes, we have 12 by 0.5 inches of steel, square inches of steel, which is 12 by 0.5 square inches. That's 6 square inches. So we took all that steel and just, you know, we'd have 6 square inches. We would have 6 of those, you know, square rods, 6 of those 1 inch square rods. Yes, that's a pretty good visual. Wait, but didn't you just say one of those rods can hold up 10 Dodge Caravans? Yeah, so we got 6 of those rods. So we can hold up 60 Dodge Caravans. Wait, but you just said like a train car is 365,000 pounds and a fully loaded, I mean, an engine is 365,000 pounds. And you just said a train car is like almost 100 tons, which is 200,000 pounds. And so, and you said 1 square inch can hold 50,000 pounds because that's the strength of steel. And you have 6 square inches. So what, 6 times 50,000 pounds? Well, that's 300,000 pounds. Okay, so can you hold a train car up? Can you put a train car in this into this this crate that we built? No, because a train car weighs 365,000 pounds, and you only have 6 inches of steel that's only going to hold 300,000 pounds. Okay, but this is but I think I just kind of blew your mind here, and I think you already kind of know the answer in the end. Um, but it's just interesting. Why I think I blew your mind is like you're like, whoa. Well, here I'm gonna get back to like why people think this is tricky because the numbers, you know, steel strong, 50,000 pounds. That's a bizarre number. I don't know how strong that is. But let's say you don't have a full inch or 6 inches of steel. Let's say you go to your hardware store and you get like a little cheapo, 1/4 inch bolt. And we already said that a 1/4 inch circle isn't a 1/4 inch square. A 1/4 inch square is way more. But let's just say our cheapo 1/4 inch bolt is a 1/4 inch square. How many square inches are in a 1/4 inch by a 1/4 inch? Well, that's 0.25 times 0.25. Or look at it this way. If I have a 1/4 inch square rod and I lay 4 flat, they'll be 1 inches wide. But then I can lay 4 tall, and that'll be 1 inch tall. And then I can kind of fill them all in. So I'd have 4 times 4. I'd have 16 of those 1/4 inch rods to equal that 1 square inch. Wait. So you're saying if I have like a 1/4 inch, threaded rod, or if you compared that to if you just pretended that it was 1/4 inch square rod, it would only be 1/16 of that 50,000 pounds you were trying to carry? Yeah. So if I have 10 Dodge Caravans, but my threaded rod, a 1/4 inch by a 1/4 inch, can only hold up one of six, 1/16. That was a little stretch there, but yeah, obviously it would have to be 1/10 of an inch. I need 1/10 of an inch to hold up, yes, 10 Dodge Caravans. Or uh, let me just say it this way: if we said a square inch of steel could hold up 10 Dodge Caravans, then 1/10 of an inch of steel could hold up one Dodge Caravan. But we only have 1/16 of an inch in a 1/4 inch by 1/4 inch steel rod. So that can't hold up a Dodge Caravan. But can a ½ inch square steel rod hold one up? Probably, Because, yeah, you can just use your brain now. Since you have something in your head, you're like, well, of course that does. But that's amazing because, before this video, if I asked you, could a half-inch by half-inch square rod of steel hold up a Dodge Caravan, you'd been like, probably not. But now you're like, absolutely it will. So let's do the math. So let's put you got a half-inch square rod next to a half-inch square rod that's like 1 inch wide, and then put a half-inch square rod on top of that. That's gonna be 1 inch tall. So yeah, you can have 4 half-inch square rods for every inch of a square rod. So you'll have 1/4 of an inch. Or if 1 inch of steel can hold 10 Dodge Caravans, this half-inch by half-inch can hold 1/4 of 10. So it can hold 2.5. So it can easily hold 2 of those Dodge Caravans. This is amazing, David. This is like the 8th thing, and you're blowing my mind. And this is like basically no longer than a lecture. I'm already at 41 minutes. This is where I'd be like, well, now go do some easy problems. But instead of that, we're going to use this full hour just to thoroughly blow that mind sky high. Because now we can go back and say, well, how much force can that flange hold? Well, let's just turn our brain off. You said 300,000 pounds. And I get how you got there. You said steel is as strong as 50,000 pounds per inch. So if I have an inch of steel anywhere, it's going to be, I can yank on it and stretch it out. I can 50,000 pounds for every inch I have. And I got 6 inches of steel in that flange that I welded together. So I have 300,000 pounds that I can put on that flange. And why I know I'm blowing your mind is because most y'all are laymen's, and that's not a like a put down, but it's good to know, because if I'm making a video for laymen's, um, well, this is where I'm going with it. Where I'm going with this, it's not a put down, but I'm saying it's just like, um, this video is also for engineers, because engineers' brains are just getting blown right now because they're just like, whoa, David, you took something that like I think is complex and you're making it just dirt simple. And you've seen an angle where now I can just look at an I-beam. Like even an engineer has got to go to like, I don't know how strong that thing is. But if you look at it in this perspective, and we're undershooting here. I mean, we're just saying it's hinged at the bottom, and it's not. It's welded full way through. But if you think we're just hinging it at the bottom, welding at the top, we'll probably get a pretty close answer. Pretty darn close, because in that first scenario of that duct tape is literally the only thing keeping that thing from falling out of the sky. But right now, we got a fully welded top flange, 12 inches wide, half-inch thick. We said it was 6 inches. It can hold 300,000 pounds. And that's so drilled into my head right now. It's just amazing, David. So you're telling me that thing can hold 300,000 pounds? But yes, but now let's go back to our leverage. Now I'm just going to give you the wrong answer. Does that mean that we can put 10 times the leverage on that I-beam and we can put 3 million pounds or something like that? No, that's the wrong answer. It goes the other direction. See, we were leveraging one way. We said if I put one of me on the end of that flange in Bozeman for this canopy with this 1 foot by 1 foot I-beam sticking out that weighs 20 pounds per square foot, 200 pounds of I-beam sticking out. If I put one of me at the end, like how much time am I going to multiply on that force on that duct tape or that flange that I welded? Well, we said 10 times. So now let's reverse it. If I say that flange can hold 300,000 pounds, how much force can I put on the end of that 10 feet? Well, divide by 10, right? Yep. And it's going to be 30,000 pounds. Okay, so what the hell is 30,000 pounds? Well, we said 50,000 pounds was 10 Dodge Caravans. Okay, so 30,000 pounds is like more than half those Dodge Caravans. So we're talking like 6 Dodge Caravans. I don't know if that's an exact answer, but that's how you do math in your head. You're like, so at the end of this I-beam, sticking out of this building, I can pull down, I can support 6 Dodge Caravans. But once I put that seventh one on, that flange is just going to break in two, hit the ground, and hinge down, and just, yeah, it's going to do its thing. It's going to break, right? Okay. So now, yes, mind thoroughly blown. I think you get where we're going, and you got there. So anytime that you're walking around and you see an I-beam sticking out of a building, you can just pretend it's hinged at the bottom. That flange, just, cut it all out. And then, just have that top flange still connected. So all you have to do is hinge the bottom, like cut the bottom hinge right in half. Put a hinge, like bolt a hinge onto there. And then continue cutting all the way up until you get to the top flange. Now you can pull down on that I-beam as much as you want, and you can calculate exactly how much you can pull before the top of that I-beam, just like duct tape, is just going to rip apart. Just going to rip apart in tension. That's another little term now. Now you know what tension is. The top of that I-beam is in tension. Or you pull down on that I-beam, it's only as strong as the tension you can put into that duct tape or that chunk of steel. And again, we had 6 inches of steel in that flange at 50,000 pounds per square inch. That was 300,000 pounds, and we were 10 feet away pulling. Now this library in Bozeman, Montana is pretty big. Maybe the front of the building flanges out 20 feet. So now how much can I put down? Well, if I said, well, that was a terrible math problem. Let's say it sticks out 30 feet. So like, whoa, that's pretty far. Like cantilevered out 30 feet? Yeah, but that's why we have 1 foot by 1 foot, steel. So let's see if this even makes sense. It can hold 300,000 pounds, and it's 30 feet out. So now I can put 3,000 pounds on the end. Now, is that a lot? No. No, 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 no. Is that, well, let's see. No, 10,000. I'm sorry. Let's do that one again. So if I know my flange can hold 300,000 pounds, because I got 6 inches of steel, each inch can hold 50,000 pounds. So that's 300,000 pounds. But I'm 30 feet out, so I got to divide by 30. 300,000 pounds divided by 30 is 10,000 pounds. Okay, so I can only put 10,000 pounds on the end, which is only 2 Dodge Caravans. Well, I mean, kind of, with passengers. Dodge Caravan stock with just me in it. I go to the dump, take my leaves to the dump. My car only weighs 4,000 pounds, but with like four or five people in, it's gonna weigh 6 people, 7 people. I don't know. It's gonna weigh 5,000 pounds. So that's 2 of those Dodge Caravans. Yeah. All right. So if my cantilever's 30 feet out, I can only hold 2 Dodge Caravans. Is that going to be enough? Well, I don't know. Maybe you put a bunch of other building material on, and you put like your metal roof in and stuff like that, and then you put snow. You know what I mean? So then you put a lot of snow on there, and maybe that snow is going to be more than the weight of a Dodge Caravan. It could easily be. So maybe you can't put a cantilever 30 feet out. See, you already came up with a scenario in your head where you're just like, yeah, I probably can't put a cantilever 30 feet out because it's going to be too much snow, And there you go. So, and that's for another video, but I'll just give you a little tidbit. Like, just in our head, like how much snow is per square foot? I think it's like 20 pounds. I don't know. But let's say all in all, let's say you just have 100 pounds per square foot, and we have 30 feet sticking out. So for every foot, we're gonna put like 100 pounds. That makes sense because maybe we're just gonna have like a party on top of this awning where everybody occupies like 1 little foot or 2 little foots, and there's 100 pounds per square feet on top of that, on top of the awning of this library. So, or let's just say you have and then just one I-beam is holding it up. So even if you just have one I-beam, so you made a cantilever, I-beam sticking out of the building, nothing else is, and you put 100 pounds every square feet, and just pretend that all that weight's at the very end. So in our scenario where you had a 30-foot length of I-beam sticking out of a building, you're going to have 30 times 100, which is 3,000 pounds. So even in that scenario, that's going to be lower than 10,000 pounds. But that's just the weight on that I-beam. Now, you're not going to put an I-beam every 1 foot. You're going to put an I-beam sticking out, cantilevered, and then another 10 feet or 15 feet later, you're going to put another I-beam sticking out. So let's say you do it every 10 feet. So you have 30 feet I-beam sticking out, and every 10 foot you put another I-beam. Well, it's not like slicing bread where you do two slices and you get 3 pieces of bread. I'm just going to make it easy for you. But if you put your I-beam sticking out of the building every 10 feet, that means that each I-beam will actually hold, the weight that you put in 30 feet long, but then 10 feet wide. So if I have snow and building material and a party on top of this, this canopy, I'll have 100 pounds per square foot. And I said it's going to be 30 by 10. That's going to be the force on one of those I-beams. And this is very crucial to this problem because you're like, why stick an I-beam out of a building that's super strong? But now you see, if you see something super strong coming out of the side of a building, you probably only need it like every 10 feet. Now, if you have something that's not that strong, you might need it like every 16 inches. That's like rafters, like a deck. Yeah, that's something kind of strong, but you need one every 16 inches. But if you're looking with these steel I-beams sticking out for a canopy, you might need one every 10 feet. And let's see if this even makes sense. So we have 30 feet long sticking out, 10 feet wide. So you got 30 times 10, but then also that's going to hold 100 pounds. All right, so that's a lot of numbers there, but let's do it. So you have 30 times 10. That's the square footage. That's going to be, well, it's 3 times 10. Yeah, 30 times 10. I don't know why this is blowing my mind, but that's 300. I just wanted to make sure. Yeah, that makes sense. 30 times 10 is 300. But then we're multiplying by 100. So we have 300. 300 times 10 is 3,000. And then 300 times another 10 is 30,000. Ah, see, the light bulb just went on. So you're telling me that 100 pounds per square foot, which would be like snow, a party, a bunch of people, the actual weight of the friggin' awning, that's 100 pounds per square foot. Maybe that's reasonable. You're telling me that if I have 100 pounds per square foot, one of those awnings sticking out 30 feet is also going to take the weight sideways of 10 square feet. And all that's going to add up to like 30,000 pounds. Yeah, where should we put the weight? Let's just put the weight in the worst possible location, right at the end of the I-beam. So instead of me hanging onto the I-beam, we're going to take all that weight and just, 30,000 pounds. Now, is the I-beam going to break? That flange, with the hinge that we did? Well, let's go back to our calculation. And I think we know the answer is pretty amazing. And I just came up with this one. This is just spitfire. I need to come up with another term like, just like spitballing and stuff like that. My character needs to really come up with another term that's just kind of more creative. I don't know. But anyway, we're just doing that thing. We're doing our thing. This is totally made up. And it's just when you make up something with just the utmost confidence, it just works out. I mean, this video will probably be under an hour. It'll be like perfect lecture. Like the bell's about ready to ring, but you don't want it to ring. You're just like, I'm in another dimension. You're blowing my mind so much that I just want to keep listening to you. So go ahead, hit that like, hit that subscribe, get more of these videos. All right. So I think we know the answer. I think we know the answer. It's like it's either going to hold or it's going to break. It's like right on that edge. We have 30,000 pounds pulling on the end of that thing, and we said our flange is six. It's 12 inches across, half-inch thick flange. That's 6 square inches. But each square inch can hold 50,000 pounds. So that's 300,000 pounds that it can hold in the flange. But we're 30 feet out. Oh, I thought the problem was actually equal, but it's not. So the flange can hold 300,000 pounds. So yes, so you need to know that. But then all you need to do is divide by the length that is sticking out. but it's sticking out 30 feet. So yes, the flange can hold 300,000 pounds, but it's sticking out 30 feet. So you divide 300,000 pounds divided by 30, and you get 10,000 pounds. And guess what? That's when it's going to break. And how much weight did we say was on it? Well, we said it was 30,000. So yes, that I-beam is going to break. Okay. But then, then you're thinking, well, it's just like, well, and I-beams aren't that way. They're not hinged at the bottom. They're just, like, welded all over. So then what's the answer? Is it double? Well, that's for another video because I don't know. But I do know that this is a great way to visualize. And I think it's close enough. Because yes, that compression in that steel also, you know, steel compresses and breaks just as easily as it pulls and breaks. So we can look at that in another video. So maybe it is. Maybe you weld it all together, it's twice as strong. Well, is twice as strong going to be enough? No, we already said we needed 30,000 and twice as strong is only 20,000. Well, how about that web? Won't that make it just as strong? Well, that web, that's the deal. That's why it's shaped like an eye. The top does a lot, the bottom does a lot. That wedge just does nothing, hardly nothing. Okay, so there's a chance that even in this scenario, um, that I-beam's not going to work out. But I will tell you, I don't think the live load limit is 100 pounds. Maybe it's or like the dead load for a building. I think it's like 40 pounds. So it's half or even a third. Let's say it's a third, and that thing will hold up. So you can have a. So let's say we were pretty good. You know what I mean? So yeah, let's say it can just hold. But are you going to make something that just holds? No. Um, you have to make it at least twice as strong, right? We all know factor of safety, twice as strong, or sometimes four times as strong. But anyway, you get the idea. But now, when you see I-beams sticking out of a building, like for cantilevers for a canopy, and you see them every 10 feet or every 6 feet, now you know. Because uh, we did it right. We have a 30 feet I-beam sticking out of our building, and but if we put them every 10 feet, like it'll just barely hold. So what could we do to double our strength? Well, we could just put an I-beam every 5 feet. Then I think you get the idea that that just doubled our strength. So we didn't have to change our I-beam because we just bought them from the I-beam shop or the metal shop or whatever, you know what I mean? And we got our I-beams. We're just gonna double them up. Not one every 10 feet, one every 5 feet. And now instead of like just barely holding that weight, now we're a factor of safety of 2. So now we learn the concept of factor of safety. We can figure out how strong is something we need and then do it that way, and then like kind of double it up, make it twice as strong. And that's an easy way to make something twice as strong, is just put twice as many things in. And in this scenario, yes, putting I-beams next to each other, um, you know, if you have them spaced out every 10 feet, and then you put some I-beams in the middle, so they're spaced out every 5 feet, that's going to double the strength. And I think that's a great place to stop. We learned a lot. I think we learned a lot. And we said that for other videos. You're like, well, now I'm curious. Like, does this, and I'm not going to mislead you. I'm going to say this is how I think of things, because if it is just double, now I know how to easily calculate the strength of an I-beam coming out of a building, and maybe I just multiply it by 2, just in my head. But I'm not quite sure. I want to be pretty certain about that one. So I want to go, because how they calculate the strength of a bridge or an I-beam or a beam in general is not based on the principle that I just showed you right now. But that principle still 100% works. I mean, in theory, yeah. If you had a hinge and then did that thing at the top, that would be definitely weaker than just having an I-beam welded together. We could all agree on that. Like, no one's going to disagree on that. So the fact that we can calculate one with almost 100% accuracy because we're using the laws of leverage is quite amazing. But is it like, I mean, there's a chance that that way of calculating is actually just very close to the actual answer of how much weight you can put on. because when it comes to calculating the weight of beams and I-beams, they only calculate them if you oh, bell's about to ring, already over an hour. But as you're collecting your bags, you can hear this last little thing on the way out the door, is that when they find the strength of cantilevers or I-beams, they just do it on how much it's going to bend. So you pull down on the I-beam, it's actually going to bend based on its shape and its characteristics. And if it bends too much, they're going to say that's the limit. So it's not like holding you know, a square rod holding up all those Dodge Caravans where that's definitely either going to hold or break. But the I-beam's going to bend, and at some point you're going to be like, well, you ever see a semi going down the road and it's just all bent out? Well, no, because we have limits and it can only bend so much. But that's why they curve them one way, so when you bend them down, they're flat. But anyway, all right, you got 4 minutes to get to your next class, and I'm taking your time, so I'm just gonna say, that's a video.